Our third common topology that we're going to consider is our feedback form. So I've drawn a simple diagram below that has feedback form, and so notice at first glance you might want to say that this is a parallel connection. But if we try to use our definition, we notice that for our G block we have a starting point over here and an ending point over here, whereas for our H block we're starting here and ending here. So in this case, these two components are not in parallel, but rather we have a feedback system where our G of S is our process and our H of S is our feedback. And of course, like we've had before, our R of S over here on the left is our input and our C of S on the right is our output. So what does this mean in a physical system? So let's say maybe we have a motor and we're telling it to rotate at a certain speed. Well, so that would be our process and our input. So the R of S is we're telling them what speed to do. The process is saying, all right, I see your input, let me do that. And it sends an output, rotate at this speed. Well, in a more advanced system, what we might have is something here that is monitoring the speed and it's feeding it back to be combined with the input to say, hey, you're going a little faster or you're going a little slower. Let's make an adjustment to get closer to what we want. So that's sort of the main idea of a feedback system. And so this signal right here after our summing junction, we're going to call this E of S. And if we have a unity gain system, that's going to be our error signal. But to keep things more general, if we don't have unity gain, we can call this our actuating signal. Okay, so our main goal here is ultimately we want to do the same thing we did with our parallel and our cascade forms. We want to find some GEQ of S that directly relates our output and our input, C of S and R of S respectively. Again, the power of that is once we have a single transfer function that represents the system, we can figure out what type of response we're going to have and maybe some more details about that particular response type, such as speed, or we'll get into some more things later, such as stability and all of that. All right, so this is going to be a little more complicated than our previous two systems, but let's go ahead and see how we can do this. So if we try to define this E of S, we can do that using this summing junction to the left. So we see we have some signal coming in, and notice I've put that this can be either subtracted or added. Most systems are going to incorporate negative feedback, which means we're going to be subtracting, but you often see positive feedback as well. And then of course we just have our R of S coming in here. So we can write an equation and we can say that our E of S is equal to the R of S input, and then we're either going to subtract or add, so minus plus, C of S times H of S. Because remember, we have C of S, we have a pickoff point, that's being multiplied by H of S, and that's what's coming in here to this summing junction. Okay, so to be consistent with my notes, I'm going to call that equation 1. And we can get a second equation by looking at sort of just the process line here. So we can say our C of S is just equal to E times G. Well, we can rearrange that and we can say E of S is equal to C of S divided by G of S. So to be consistent with the notes, I'm going to call that equation 2. So what we can do is we can substitute this equation 2 into equation 1. So we're going to substitute there. And ultimately what we want to do after we substitute is we're going to want to solve for our output over our input, because by definition, that's our transfer function. So C of S over R of S is what we want to solve for. And again, by definition, that's going to give us our equivalent transfer function, G sub EQ. All right, so let's go ahead and do that. So we have, if we substitute, we have C of S. And so actually I'm going to go ahead and start dropping our of S. So we have C divided by G is equal to R minus plus C times H. All right, well, we can multiply that G through and move some things over such that we have a C plus minus CGH is equal to R times G. And I'm kind of going through that a little quick. If you have any questions about that, definitely let me know. So now on the left side, we can factor out that C. So we can say C times 1 plus G times H. And of course, over here, we just have R times G. Just to make that explicit, we'll show it like that. And now we can easily get our C divided by R that we wanted. So I'm going to add my S's back in. So we have C over S divided by R over S. And that's just going to be G divided by 1 plus G times H. Or, sorry, I've lost my minus, plus minus. So we have G of S in the numerator from the right side here. And now we have 1 plus minus G of S times H of S. And so this is going to be equal to our GEQ. Okay, so this is our sort of basic equation for our equivalent transfer function. One thing to note that often trips people up is we started up here in our block diagram with a minus plus for our feedback, and in the equation for our GEQ, it became a plus minus. So what that means is if we were to have, let's say up here we had, this was negative feedback, then in this equation, we're going to use a positive sign. We're going to be adding the G of S, G times H to the 1 in the denominator. So make sure you don't mix that up. One other thing I want to mention is that this term in the denominator is oftentimes an important parameter as well. So this G of S times H of S is something called our loop gain or our open loop transfer function. And so we're not going to deal too much with that in this class, but definitely the electrical engineers, we're going to come back and we're going to talk about this a lot in applied electronics. And we're going to talk about how we can relate that to systems and determine stability of systems and all kinds of fun things from that. Before we move on to looking at examples of how we can use these three basic forms, our cascade, parallel, and feedback, I do want to mention one thing about how we're sort of idealizing connections of systems.